Hey, good morning, everyone. So we're gonna get started on probability today. So do you have any question from the previous chapter or anything from your homework? I'm more than happy to go over that.
Professor, this is Asma.
Asma, yeah.
I don't know if you remember my email, what I said in my email, but I'm not able to stay in the course today. Is it fine if I would just watch the recording? Because I'm still sick.
Yeah, sure, definitely, Asma. Yeah, I fully understand, right? Feel free to leave if you do not feel well. Okay.
All right, thank
About
you.
it. You can always watch the recorded video after that.
Thank you.
All right, cool. Besides that, any other question? Let's say if you have any homework question, I could help you with that, right? You can just tell me the section number and then we can go to that. And there will be no Excel project today. So we're gonna mainly concentrate on the lecture, right? On chapter 4. Okay, so since nobody have a question, so we're gonna get started on chapter 4. And let's provide let me provide a quick summary of probabilities, chapter 4, probability. And actually, the probability has very wide application in real life. And let me just pose a question. Let's say, what is the chance? By the end of the chapter, you'll be able to figure out this. What is the chance of winning? Mega Million? This is all of these lottery companies provide these games, right? Like Mega Million is one of them, and you probably wonder, what's the probability of winning the Mega Million, right? Since sometimes we heard somebody win the Mega Million, but in order to get a better idea of how this works, you probably want to figure out the probability of getting this outcome, meaning winning a Mega Million. Okay, so now, so let me just go to the basic concept of probability, and then by the end of the class, I will show you, how to find the probability for this particular case. All right, so all the fundamental terms start with the procedures. Okay, fundamental concepts. First is procedure. So procedure is like action outcomes whose outcome is random, right? Action whose outcome is random. And for example, that's a very simple case is rolling a die, roll a die, and it could be a flip a coin. Okay. If you roll a die, we basically have 6 outcomes, right? An outcome could be 1, 2, 3, 4, 5, 6. Assuming we roll in a 6-face die. Okay. And if you flip a coin, you have 2 outcomes, right? Head or tail. This is the most important concept in probability. So basically, you have action. Roll the die is action. Flip coin is action, and then the outcome is random. So you never will have certainty that you get guaranteed to get certain outcome, right? Like flip coin, you never know. You either get a head or tail. Same idea. So outcome random outcome, very very crucial to understand the probability random outcome. Okay. And that's first important concept. Second one is the event. Event is any collection of outcomes of procedure. Outcomes of procedure. So event come from the procedure. For example, let's say you roll a die. And an event could be getting an even number. So based on this description, we have 3 outcomes satisfy this result. It will be 2, 4, and 6. They're all even numbers, right? So this is what they call the event. Okay. Oh, you can roll the die, get an odd number, right? Same idea. That's also an event. Okay. So first one is this: roll the die and getting an odd number. And the number satisfied this outcome will be 1, 3, 5. Also, you can say something like roll a die, getting a number bigger than 4. Then this event basically have 2 outcomes, 5 and 6. Right? Okay, so you can come up with a lot of events, right, based on the procedure. So I'll just give you some example of this. The event is based on this particular procedure. The third important concept is what we call a simple event. So simple event is an event cannot be simplified further. An event cannot be simplified further. For example, it could be for flip a coin case. You get a head. Then getting a head, right? We cannot break that further because that's a simple event. So you can also say getting a tail. That's a simple event. Also, like so, this is one of the example. Another example. You roll the die and get a 4, right? Now this is also a simple event. Just cannot break further. And the fourth concept is compound event. So compound event is an event that could be broke down further, or it's a combination of simple events. Okay, so let me give you an example. Like the example I mentioned earlier, you can roll the die and get an even number. Get an even number. And this is a compound event because we have 3 simple events, which is 2, 4, and 6. So this is exactly idea of the compound event. So each one of these is a simple event, but you put them together, it becomes a combination of simple events. Then it is a compound event. And now the next concept is a sample space. Sample space of a procedure. Basically, sample space includes all possible outcomes. So for example, when you roll die, then sample space will be 1, 2, 3, 4, 5. And 6, right? All 6 possible outcomes becomes a sample space. And when you flip coin, then the sample space will be head and tail. Okay. So this is basically sample space includes all possible outcomes, right? And typically we use this notation to represent the probability, which is P represent probability. And then we use A, B, or C. Represents a specific event. For example, P of A represents probability of event A. So obviously P of C will be represent probability of event C. Okay. So this is most important concept, and basically they have two procedures to define the probability. Those two are very important. Okay, so in terms of defining a probability, two procedure. First one is called relative frequency approach. Under relative frequency approach, you observe procedure a large number of times and then counting the number of times that event A occurs. So observe event procedure a large number of times. And then count the number of times that event A occurs. So this probability could be P of A equal to number of times A occurs over number of trials. A good example is the very first place when the mathematician discovered the probability of getting a head or tail is by using this particular procedure, right? Relative frequency approach. So for example, if you flip a coin 1,000 times, and then count number of times show up. And this is what we call the relative frequency approach. And typically you'll get something around 500, right? 500 heads and 500 tails. And that's why we know that probability of head, H represent head, will be number of times heads show up. over number of trials. In this case, most likely you will get about 500 heads, 500 tails, and over 1,000. And that's why we get a 0.5 as a probability. And that's why we're using, when we talk about probability of head or tail, they always becomes 0.5 or 50%. Probability of head, M equal probability of tail, they both 0.5. And this comes from the relative frequency approach. We also have another approach called classical approach. Second approach, classical approach. Under classical approach, if a procedure has n simple events, that occurs equally likely, meaning they have an equal chance to occur, equally likely. And there are different ways event A could occur. Then probability of event A equal to number of ways A could occur over number of simple events. Number occur over number of simple events. So for example, very simple example, we talked about this earlier. When we roll a die, and then get an even number. See, so in order to calculate this probability of even number, right? We know that even number, getting even number could be 2, 4, or 6. So we have 3 possible outcomes here. So number of ways A could occur will be 3, right? And number of simple events will be 6, because the sample space is 6. So 3 over 6 becomes half, or 50% as well, 0.5 or 50%. So in terms of expressing the probability, you can use fraction, decimal, or percentage, right? Depends on the need. If you feel like one of them is better in terms of expressing the probability, then you can use that. This is exactly the concept of the classical approach, right? So you focus on the specific procedure and then analyze, all those simple events, and then after that we'll be able to get the designated outcomes we want to have. Okay, and that's a classical approach. The third methodology popular out there is subjective probability. And a lot of this professional service, like weather forecasting or like earthquake forecasting, right? Those are the subjective probabilities, right? Because this probability is defined, the probability of event A is found based on knowledge of the circumstances, of expertise of circumstances, like weather forecasting or earthquake forecasting or any like similar nature, anything similar nature, all the probabilities are defined based on the subjective probability defined based on the knowledge or expertise of certain conditions. Or like predicting the economy, right? That's also another example. Predict economy, okay, weather forecast. That's why it's very difficult to have a 100% accurate prediction in terms of weather, in terms of economy, because of the nature, right? Because it's based on the knowledge, expertise. It's not we don't have a certain, we don't have a certain way to make sure we have the right probability. That's why it's always approximate, right, result, weather forecasting. Okay, those are the examples of subjective probability. Now, let's take a look at this. For example, let's think about this. Let's say example. Well, let's say you flip coin twice, and then what will be all the possible outcomes? What is the sample space? Flip a coin twice, 2 times. What is the sample space? Anybody have a suggestion? We know flip a coin 1 time, we have 2 outcomes. What if we flip coin 2 times? Okay. So first of all, I'm going to give you a very general idea, right? How to tackle this type of problem. So you can view that as this. So those 2 events are independent, right? Meaning getting the first head does not guarantee you getting the second head. Same idea. If you're getting the first tail, it doesn't guarantee you're going to get second tail. All right, so this is the first and second. And you look at the outcome for the first trial, right? So first trial, we have 2 outcomes. Second trial, you also have 2 outcomes, right? And since they are independent, so you multiply them, you get 4 outcomes. Okay. So we know that should be 4 outcomes. But now let me show you a way to construct this, construct sample space. So think about this. So we can construct a sample space like this. So we can have 2 heads, right? And you can have 1 head on the first trial, tail on the second trial, and then tail on the first trial, head on the second trial, and the last one will be tail. Okay, and that's exactly 4 outcomes, right? It matches with our analysis. Okay. And the third way to confirm this is constructing a tree diagram. Okay, look at this. So this is a starting point. We start here, and after first trial, we have 2 outcomes, head and tail. Okay, this is after first trial. When you flip the coin for the first time, you either get a head or tail, and then flip the coin second time, this is second time. And if you look at it, you still have head or tail, right? Outcome is always either head or tail. So now this is like rotating the tree like 90 degrees, clockwise, right? So you come up with this, and that's why it's called tree diagram. It look a lot like a tree. So head and tail, the second outcome, tail head, and tail. So it basically is just follow the direction of the tree, right? The branch of the tree, head could become first outcome, head tail become second outcome, and tail head third outcome, tail fourth outcome. So now we come up with all the possible outcomes. And totally up to you, right? So you can pick any method here to come up, construct a sample space. Okay, and so this is a very popular one. So now let's look at it more carefully. What if you flip coin 3 times? What would be the sample space? And let's list all the possible outcomes. Give you a couple minutes, think about this, and I will show you the results. Meanwhile, I'm taking a screenshot of the tendons. Okay. All right, anybody figure out the answer? How many possible outcomes are there? All right, so let's take a look at it. Right? Okay, so we have a flip coin 3 times. This is first time, second time, third time. Okay. So now our first on the first trial, 2 outcomes, 2 possible outcomes. Second trial also 2 possible outcomes. Third trial 2 possible outcomes. They're all independent, so it's 2 to the third power. So that's 8. Okay. So that means we have 8 possible outcomes, and you can use this to guide our all these possible outcomes. So now let's think of how to construct the sample space, right? How to list all the possible outcomes here. So now let's just focus on number of heads. Let's say you just worry about number of heads. So based on this particular category, then we have first one, 3 heads. Okay. Second category will be 2 heads, meaning 1 tail, right? And then third one will be 1 head. The last one will be 0 head.
I'm sorry, what is this ABCD? Where are these coming from?
So you just focus on the number of heads, right? Like, remember, when you flip coin 3 times, you either get 2 extreme cases getting 3 heads or 3 tails, right? So getting 3 heads, we have that here, right? And then getting 3 tails meaning 0 heads. And then anything in between are possible. So 3 heads, 2 heads, 1 head, and then 0 head. Does that make sense? Think of 2 extreme cases, 3 heads, right? Definitely head, head, head. Okay, 3 heads. And then tail, tail, tail. That's another extreme case. That will be 0 head. And then in between these 2 extreme cases, we have 2 heads, 1 head. And this is one way to look at the sample space. I just want to show you. You can also focus on number of tails. That also works. But let's see, 3 heads, it's pretty obvious, right? It will be triple head. With 2 heads, now we can think of 2 heads, 1 tail, meaning. So the tail could be appears on the first spot, right? The tail could appear on the second spot, and the tail could appear on the third spot. You see, first location, first spot, second spot, third spot. So we're just allocating that particular tail here to generate 3 outcomes. Okay. And then 1 head, very similar. You're gonna have head on the first spot, meaning 2 tails. Head on the second spot, 2 tails. Head on the third spot, so 2 tail on a row and then head. Similarly, 3 outcomes, right? Okay, so we're allocating the head on a different location to generate 3 outcomes here. 0 head, meaning 3 tails, so tail, tail, tail. As you can see, it should be 1 plus 3 plus 3 plus 1, 8 outcomes, right? And here we got 8 outcomes. Okay. By looking at in this particular angle, right? Like focus on the heads. We can also focus on the number of tails, no problem. Let's say now we just look at we're just concerned about number of tails. Okay. Okay. Now 2 extreme cases, right? You either get 3 tails, triple tails, meaning 3 tails. Or you get 3 heads, meaning 0 tail. And anything in between possible. So we get 3 tails, 2 tails, 1 tails, and then 0 tail. So look at this, 3 tails, first outcome, and that's obvious, right? Will be T, 3 tails in a row. Second outcome will be 2 tails. 2 tails indicating 1 head. So now we just have to allocate the head. So head could appear on the first spot. Head could appear on the second spot. Head could appear on the third spot. And you see 2 tails is exactly 1 head, right? If you look at the outcome here, they match. Okay. And then 1 tail, meaning now we are allocating the tail. So tail on the first spot, tail on the second spot, and tail on the third spot. You see 1 tail, exactly 2 heads. Again, the outcome will match. Okay. And third one, this third one, and last one will be 0 tail. That means 3 heads, right? Head. Now, based on this logic, we also come up with A outcomes. So no matter how you look at it, we always end up with the same result, right? Now, again, I'm going to show you the systematic method of getting all these outcomes. It's pretty, and this is not that obvious because you have to analyze, the outcomes in different categories. In this case, it depends on your focus. If you focus on the heads, then this is how you will tackle that. But if you focus on the tails, this is how you tackle that. But again, we can use a little bit more systematic method to solve this, but there's an intrinsic logic behind it, right? Kiara, you have a question?
Yeah, so would the sample space be the same for every possibility?
Yeah, for this particular case, it is. Yeah, sample space will be the same, right?
And if you had a dice, would the sample space be the same?
Yeah, it will be slightly different, but I'm gonna get to that in a second. Yeah, when we finish this one, and then I'm gonna give you another example. After that, I will talk about the dice a little bit, like flip. When you roll the 2 dice, right? That becomes more interesting. If you roll 1 die, it's pretty straightforward. When you roll 2 dice, 3 dice, then it becomes a lot more interesting. Yeah, I'll get to that. Okay, in a second. All right, now one more time, tree diagram. I just want to give you all these different tools you can utilize, to understand, the outcomes and also the probabilities. Okay, tree diagram. So very similar to constructing the tree diagram and rolling flip a coin twice. Right now it's 3 times. Okay, so we start here. And this is first. Okay, flip it. Roll it once. Flip it once. So you get head or tail, right? That's always the case. Second time. This is the second time. Still head or tail. Now third time. Still head or tail, right? No difference. But we have more branches here because when you flip the second time, you have more branches compared to the first time. And now third time you have again, you double that. Head, tail, head, tail, head, tail. And again, we just follow the branches of the tree, right? This, we get triple head. 3 heads, okay. Now if you look at it, head, tail, second branch, right? Head, tail. And now the third one will be head, tail, head. If you follow the branch of the tree, head, tail, head, tail. This one, and this one, right? And then head, tail, tail will be 4th outcome. So this is first half of the branch. And second half, bottom half, start with the tail, and get tail, head, tail, head, head. And second half of the branch always start with the tail. So tail, head, tail. Okay. And tail, tail, head. And now the last one will be tail, tail, tail. Again, A outcomes. And it will match with the outcome from previous two analysis, right? So no matter what method you use, you always end up with the same result. Okay. So now I'm going to ask you this question. What is the probability of getting two heads? Getting two heads. What do you think? Any suggestion? Okay, so you just go through the outcomes, right? And then see how many outcomes satisfy this condition, two heads. Look like this one satisfied, right? Head, head, tail, tail, head, and tail, head, head, right? Those three outcomes satisfy this event. So we know that will be 3 outcomes out of total 8. So it's 3/8. Okay. Very similar. What's the probability of getting one tail? So now you also go through this other list, right? Look at how many outcomes satisfy this one tail. Okay. One tail, this one, right? One tail, one tail, one tail. Okay. Still, right? 3 out of 8. Okay. So two heads, one tail, they are actually they refer back to same possible outcomes. Okay. And how about probability of getting 3 heads? You look at it, only one outcome satisfies the 3 heads, right? Which is head, head, head. So it's 1 outcome out of total 8 outcomes, 1 over 8. Okay. All right. Any question on this? Another example to think, right? Let's say a couple, right? Second example, two. A couple plans to have 3 children. And what is the probability of getting two boys and 1 girl? What is the probability of having 2 boys and 1 girl? And this is very similar to head-tail case, right? When a couple have the first trial or second trial or third trial, there are 2 outcomes, right? Either have a baby boy or baby girl, right? So it's very similar to the one we just discussed. And I really want you to understand this and figure out the results. 2 boys, 1 girls. Let's see what is the probability of having that. I'll give you a couple of minutes. Think about this. Any suggestion?
Is it 1/4?
Okay, it's very, very close. Yeah.
Dang.
It's yeah. So
Or is it 2/6? I got two different answers. I was unsure because I thought I had boy, girl, boy
mhm.
like twice. So that's how I went from 2/6 to 1/4.
Okay. So you definitely in the right direction.
Okay.
One more time, we're gonna just look at a big picture really quickly. Three
Mhm.
child, right? First, second, third. If you look at just outcome itself, right? For the first child, how many outcomes? Two possible outcomes, right? Either a boy or girl. Okay. And then the second child, still two outcomes, right? Third child, two outcomes. And they have no impact on each other. Meaning getting a first boy does not guarantee you're gonna get a second boy or second girl, right? It has no guarantee at all. So that means they are all independent. So if you multiply all these outcomes from three different trials, will be A outcomes, right? So we know that it should be A outcomes. And now just follow similar analysis from the previous one. Now we can just focus on, let's focus on number of girls first. If you just focus on number of girls, we have two extreme cases, right? either getting 3 girls, girl, girl, girl. So G represent girl, B represent boy. Okay, so meaning one extreme case is all 3 are girls. Second extreme cases is all 3 are boy. So we have 3 girls and then 0 girl. Now very similar, anything between are possible. So we have 4 major categories, right? 3 girls. That means we get girl, girl, girl. Okay, that's good. And second one is 2 girls. So that means, and 2 girls meaning 1 boy. So we could just allocate that boy. So boy could be the oldest one, right? The first spot. So boy, girl, girl. Could be girl, boy, girl. Could be girl, girl, boy. First spot, second spot, and the third spot. By just allocating that boy, right? And then we can also allocate the girl here. If you look at 1 girl case, now we have only 1 girl, meaning girl could be on the first spot. Okay, get girl, boy, boy. Girl could be on the second spot. Girl, boy, girl, boy. Okay, and then girl could be on the third spot. So 2 boys in a row and then a girl. So boy, girl, boy, and then boy, boy, girl. First spot, second spot, third spot. Okay, and the last scenario will be 0 girl. Then we know that must be all boys. Now, if you look at combine all these possible outcomes, we get A outcomes. All right, so this is focusing on the number of girls. You could just focus on number of boys, right? We'll get a similar analysis, but so if you focus on number of boys, and again, we have 2 extreme cases. First one is all boys, so 3 boys. Second extreme case is no boy, right? All girls, so 0 boy. So these two are, it's like identical approach, but just based on different focus. So right here we get 3 boys. We know that must be boy, 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 right? No doubt for that. Second one is getting 2 boys. So the girl, so now we can just simply allocate a girl, that 1 girl, because it's easier that way. So girl goes first, girl goes second, and girl goes last. So 2 boys in a row and then girl, right? So first spot, second spot, third spot. Okay, and then we have 1 boy. If you look at that, we just have to allocate that boy, right? So it could be boy on the first spot. Right? Boy is the second child. Okay, so girl, boy, boy, a girl. Okay, and then boy could be the third child. Okay, first child, second child, and third child. Right, 3 different outcomes here based on that category. And the last one, the last major category is 0 boy, meaning all 3 girls. And it does match, right? See, this one match this, meaning 3 girl, 1 boy, they are same thing basically. 2 girl, 1 boy, exactly the same, right? 2 boy, 1 girl, they actually complement each other. So that means the same thing. And then 0 girl, 3 boy, they are the same. Okay. All right, so this is just based on the outcome in different categories, you can generate all 8 outcomes. And now the last procedure we can do is tree diagram. Okay. And this is very helpful, right? In terms of dealing
Sorry,
with.
do you mind just scrolling up for a second?
Huh? I'm sorry?
Do you mind just scrolling up for a second?
Sure, definitely. Yeah. Me here, right? Okay.
Okay, so even when we focus on the boys,
Mhm.
there could be 6 outcomes, but those don't go into play because we're focusing on the girls.
No, actually, you can just focus on the boys, right? You can pick either one of these.
Okay.
I just show you both results to convince you they are the same thing.
Okay.
They are exactly the same thing, but you look at it from different perspective, right? You can just focus on the girls, you get A outcomes, no problem. That's totally fine. You can look at just focus on the boys, you also get A outcomes, right? No problem, same results, right? But if you compare all these each individual result, they are exactly the same. You see all 3 boys, all 3 girls, anything in between. They matches perfectly. Yeah. Okay. Yeah, just show you different. I probably show too much, but yeah, I just want you to see all these different methods of tackling the same problem, so you have options. You know, when you work on the actual problem, you also have options to find out the result. Okay. And here, tree diagram, similarly, we start here. Now, first child, right here, we know that either a boy or girl. Okay. By the time we get to second child, still the outcome doesn't change, right? Either a boy or girl. So it's like 2 dimension, right? It only has 2 dimension here. And the third child, still 2 dimension, right? It doesn't change. Either a boy or girl, right? No other possible outcomes. Now you follow the branch of the tree. First branch, boy, boy, boy. The 3 boys. Second branch, boy, boy, girl. Okay. Third branch, boy, girl, boy. Boy, girl, girl. Fourth branch. And this is the first half. You see, all start with the boy, right? And the second half, you start with the girl, girl, boy, boy. Okay. Girl, boy, girl. And girl, girl, boy. Then we're almost there. Last one will be girl, girl, girl. Start with 3 boys, end up with 3 girls, right? Anything in between. Okay, they all listed 8 outcomes in total. So now if you look at just 2 boys and 1 girl, we still haven't get to the final answer yet, right? So we want 2 boys and 1 girl. And we just need to match. How many outcomes match that? This one match, right? 2 boys, 1 girl. 2 boys, 1 girl. 2 boys, 1 girl. Okay. And as you scan through all these outcomes, we see 3 outcomes satisfy this event out of total 8 outcomes. So it's 3 over 8. Yeah. Okay. And any question on this? And very important problem, right? To help you understand the basic foundation of the probability, and also, you know, how to find the probability using a systematic method. Okay. And now, as I mentioned, I want to talk about the rolling 2 dice, right? That's also very interesting problem. If you roll 2 dice, die in a row, 6 phase, right? Again, in a row. What is the sample space? If you roll 1 die, we know that roll 1 die, you get 6 outcomes. 1, 2, 3, 4, 5, 6. And if you're rolling 2 dice, now it's slightly different, right? And I'm going to show you this table to help you understand this. Okay. It should be 6 by 6 table. So think about this. So 2 dice. You roll the die twice, right? This first die, second die. Let's look at the big picture here. When you roll the first die, you get 6 outcomes, right? When you roll in the second dice, you get 6 outcomes. And they are independent, meaning getting a 6 on the first spot does not guarantee you getting a 6 on the second spot, right? The outcomes are random. So that's the nature of this procedure. So 6 by 6 should be 36 outcomes. So keep that in mind. We're going to look for 36 outcomes. Okay. And now let's start with the table really quickly. It should be a 6 by 6 table because 6 by 6, 36, right? All right. And let me show you how to construct all these outcomes step by step. So the first one, if you look at the first one, 1, 2, 3, 4, 5, only one more. Okay. You can also try it on your own, right? It's very interesting thing to do. Let's go back. Let's start here. So the first outcome could start with a 1, right? Meaning you get the first one is 1, the second one is 1. Okay. Now you fix the first outcome. It's always going to be 1, right? And second outcome could be 2. Third one could be 3. Fourth one could be 4, and 1, 5, and 1, 6. Now if you look at it, we're fixing the first outcome here, keeping that as 1. Okay. And then we vary in the second outcomes, right? From 1 to 6. Okay. And then second category is fixing the first one as 2. Now varies the second outcome. It could be 1, could be 2, could be 3, could be 4, could be 5, could be 6. Right. So again, you're generating 6 outcomes under that major category by fixing the first outcome. Third outcome, fixing the third outcome. The first one being 3. Now you see 1, 2, 3, 4, 5, 6, right? You see the logic behind it. Okay. Again, varying the second outcome, 1, 2, 3, 4, 5, and 6. Okay. Again, we get 6 outcomes. That's where this 6 is from, right? Now the fourth one, fixing the first one as 4. So 4, 1, 2, 3, 4, 4, 4, 5, and 4, 6. And then the fifth category is 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. The last major category is 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Okay. Right, as you can see, 6 rows, 6 columns, 36, right? So this is exactly the sample space. Okay, so you get a sample space, 36 outcomes, and outcomes listed in this. Now, let me ask you a quick question. What is probability that combined total is less than 6? That the combined total is less than 6. Meaning you adding the two numbers you get, which is less than 6. How many outcomes satisfy that? Combined total less than 6. Okay. So you're gonna look at all these possible outcomes, right? Combined total less than 6. Any suggestion? You can scan through these, right? Also, look at this, right? Look at this line right here. Look at this dashed line. Okay. You see, this is combined 6. 5 plus 1, 6. 4 adding 2, 6. 3 adding 3, 6. 2 adding 4, 6. 1 adding 5, 6. And then everything above it, right? All these outcomes above it is less than 6. You see, 1, 1 is less than 6. 1, 2, 1, 3, 1, 4. 2, 1, 2, 2, 2, 3. 3, 1, 3, 2, 4, 1. Right? So you look at that, that's how many outcomes? 4 plus 3 plus 2 plus 1. Yeah, that's exactly 10 outcomes, right? So 4, 7, 9, 10. So that means we have 10 over 36. But by drawing this diagonal line, we know that everything above that will be less than 6. Okay. So this outcome is probability of getting combined total less than 6 is 10 over 36. If you simplify that, it will become 5 over 18. And but having this sample space definitely help you tackle any problem you come up with, right? Let me just, yeah, that's just what this is. Any question on this this example?
Would 36 be the sample size?
Yes, it is, right? We have
Okay.
36 exactly. Right?
Thank
And if you want to list all the possible outcomes, you should list the entire table, right? From 1, 1 all the way to 6, 6. Again, those two are extreme cases, right? Getting the smallest numbers or getting the largest numbers in a row. Yeah. Okay. Very good. So let's move on. More concept on probability and impossible event. Right. Let's talk about impossible event and certain event. I'm gonna give you a very simple example. What do we mean by impossible event? Meaning basically probability of event is equal to 0. This is impossible event, right? Probability equal to 0. So one good example is Thanksgiving. What is probability that Thanksgiving fall on a Wednesday? What do you think? That Thanksgiving Day.
That's an impossible event.
Exactly, right? So this exactly show us what is impossible event. Thanksgiving Day fall on Wednesday, it's impossible. It never happens, right? So that's why it's impossible events. And that's why the probability here is Thanksgiving on Wednesday, it's equal to 0. Okay. And a certain event, meaning the probability is always going to be 1. So probability of this event, omega, right? This is what they call omega 1. It's bound to happen. So what is probability that Thanksgiving Day fall on Thursday? It's bound to happen, right? So definitely it's going to be 1. So this exactly tells us distinguish the impossible event and a certain event. Yeah. So Thursday, that's a certain event. It has to happen. No, it's 1. Okay. So that just give you how to distinguish those two very special events. And also we have complement event. Okay. Meaning two events complement each other, right? So event A and event A with a subscript C indicating complement of event A, they are complement events. And the following rules happens: probability of event A plus probability of complement of event A, that's equal to 1. And some textbook using this notation: probability of event A plus complement, could put a line on top of event A. That means complement of event A. That's equal to 1. So either notation you like, right? And then basically just A of C indicating complement of event A. And then A bar also indicates complement of event A. Same thing, right? Complement. Event. And then very simple example. Let's say you roll the die once. And the complement event, what is the complement event of getting all even numbers? What is the complement? Of having even numbers. So complement event of having even number will be R numbers 135. And if you summing up the probability of having even number and R numbers, probability of even number plus complement event probability of R numbers, we know that probability even number is 3/6. Probability of R number is 3/6. Then it becomes 6/6, which is actually 1. Okay. That proves, they also give you idea, you know, that when you sum up the event A, complement event A, they sum up to 1. Okay. All right. Now, the next thing I want to talk about the compound event. So addition rule and then multiplication rule, right? So addition rule. So compound event, the addition rule applies to compound events. Compound event is event includes two or more simple events, right? Compound event combines two or more simple events. I'm going to give you a couple of notations, very important notation. This one is intercept, A intercept B. Let's say we have even A, even B. They intersect each other. So intersection of A and B. Even A and even B. And I mean, in reality, this means both A and B occurs. This is the meaning of that. And second notation is called A union B. And that means it's union A and even B. In this case is in reality, what this means is either A or B, even A or even B occur, both occur. Either one of these or both occur at the same time. Okay. All right, so now let me show you this in the Venn diagram, right? So you'll be able to analyze, this is what they call a Venn diagram. Basically, you have a rectangle box representing basically the sample space, right? So this whole rectangle box indicating the sample space. Now we have event A here, event B here. It's within the sample space. And here representing the A-intercept B is this small portion, the common section here, right? This common section here, this indicates probability of A intercept B. Both A and B occurs at the same time, so this middle here. Probability of A union B. With this portion here, so I'm going to use a different color, right? So to represent this, let me get a different color. Okay. A union B, meaning everything in A. Okay, so A here, everything in B, including the common section. All right, so this is basically the green one represents A union B. Okay. Now think about this. If you want to find out what is total probability of A union B, okay, so let me draw another Venn diagram. Keep it separate. So let's say event A, event B. Okay. Now we want to find out what is probability of A union probability of B. So if you do probability of A adding probability of B, meaning you adding probability of A and probability of B, assuming they have intercept, right? The intercept between. And when you do this, actually, you add in the common section twice. So this is area 1, right? This is area 2 for belong to event A. And then area 2 and area 3 belong to event B. So now you just simply adding probability of event A, adding probability of event B. You're adding section 1, adding section 2, right? Those two sections. You're adding probability of B, you're basically adding section 2 and section 3. And by combining them, we add in the section 2 twice, right? Section 2 is what we call a common section. So that means we get it subtracted once. That's why we get A intercept B subtracted from the combined total. So this is exactly what they call the addition rule. Okay. Any question on this? Yeah, very good. Okay, so this is addition rule. Maybe let me just take a look at the application of this. Okay. All right. Let's say here. Let's say this. For example, so event A has following numbers, right? 1, 2, 3, 5, 7. Event B has 2, 5, 7, 11. Now, you want to find out what is the probability of event A union event B. All right. So applying this addition property, right? Event A will be so you combine total numbers here. So probability of event A, you have 5 numbers here, 5 numbers here. That means total number, let's identify total numbers. So they are repeating numbers, right? So 2 is repeating number, 5 is repeating number. So you do 1, 2, 3, 5, 7. And then Yeah, 7 is a repeating number. Okay. And adding 9 and 11 right in the back, now we get total of 7 numbers. Okay, 7 numbers here. So probability of even A plus probability of even B, subtracting the intercept, right? They have intercept, A intercept B. They have a common numbers, that means intercept. So total numbers here, it's 7, right? So first one, probability of even A is 5/7. 5 numbers out of 7 number. Probability of even B is 5 numbers out of 7 number. And now if you're adding these two, 5/7 plus 5/7, you get 10/7. And we know that it cannot be true, right? Because total probability can never exceed 1. And this is bigger than 1. So this is impossible. Impossible to happen. Because we have a common numbers for those two sets. The first set has 2, 5, 7. Second set has 2, 5, 7. So this common section is 3, right? 3 numbers out of 7. So by doing this, we end up with 10/7 minus 3/7. That turned out to be 7/7. Okay. And that's 1. Now that 1, it's reasonable result, right? The total probability could only be 1. Right? And so this is exactly the application of the addition rule. And if you want to list in the Venn diagram, right, we can easily list this in the Venn diagram really quickly. You can do this. So the common number is 2, 5, 7 for both even A and even B. And for the remaining number for even A will be 1 and 3. Remaining number for even B will be 9 and 11. Okay. So that's how you allocate all those numbers with the intercept and then anything else other than the intercept. Quick demo of the addition rule. And there's some problems in your homework assignment about the addition rule and the multiplication rule. Okay. Multiplication rule. Actually, we already applied some of this concept. So basically, if two events, if event A and B are independent, meaning they have no impact on each other, are independent, then probability of even A intercept B become probability of A multiplied by probability of B. Meaning A intercept B, meaning A and B occur at the same time. Both occur at the same time. Okay. And this is basically probability of A times probability of B. For example, let's say this is what they call the multiplication rule when they are independent. Example, if let's say you've rolling 2 dice, what is probability that the first number is even, the second number is larger than 4? What is probability? The first number is even, and second one is larger than 4. second number is larger than 4. So basically, we are looking at the intercept of both, right? So will be probability of a first even, both occurs at the same time. Intercept second larger than 4. So these two events are independent, right? Getting the first even number does not guarantee you're going to get a second number larger than 4. Okay. That means they are independent. So you're looking at probability of getting first number even, times probability of getting second larger than 4. Okay. First even, we know that when you roll the die once, we have 6 outcomes. 3 of them are even numbers, so 3 over 6. Multiply by second larger than 4. Larger than 4 must be 5 and 6, right? So meaning 2 numbers out of 6 satisfy that. First even will be 2, 4, 6. Second larger than 4, then becomes half times 1/3. Then become 1 over 6. And we actually can list all these possible outcomes, right? To verify this, you see, we could be 2, 5, right? First outcome satisfy this, even, first even, second larger than 4. 2, 6, and 4, 5, and 4, 6. And then 6, 5, and 6, 6. These are all the outcomes satisfy this first even, second larger than 4. We get 6 outcomes out of total 36 outcomes, which is exactly 1 over 6. So you look at it from a different perspective to confirm, you know, this multiplication rule applies here. That's how you confirm that, right? Confirm. Okay. And then the last concept I want to talk about is today is conditional probability. So let's look at it, right? Conditional probability. Right. Conditional probability. So the conditional probability of the event A, given that event B occurs, is denoted by this notation, probability of A, given that B, with the vertical line between B occurs. Assuming event B has some impact on the event A. So that means when event B occurs, then the chances of event A occurring, you know, changes. So this A, given that B occurs, will be probability of A and B over probability of B. So A and B is basically A intercept B, right? Over probability of B. And let me give you an example, and let's take a look at how to apply this conditional probability. So let's say we have a 2x2 contingency table here. We get subject, and we have two categories. Pregnant, we get pregnant subject or not pregnant subject. And we have 2 general outcomes, right? First outcome is test positive. And test negative. Let me put in the numbers here. So it's 80. That's going to be 4, 5, and 11. Okay. And this is what they call 2x2 contingency table. 2x2 contingency table. This is a very famous table, right? In any in biology field, in a lot of different fields, has a very wide application in the real world. Now here, based on this table, we can analyze this table really quickly, right? And then get this total. Let's get a row total and then column total. All right. So the first row total, 85. What does that represent? Second row total is 15. First column total is 84. Second column total is 16, right? And then combined total, what will be the combined total here? What is total subject being surveyed in this particular experiment?
Is it 100?
Exactly, very good. It's 100, right? So meaning they survey 100 subjects and they break down the subject in different categories here, right? So we have a pregnant subjects and not pregnant subjects. And we have two major categories here is test positive, test negative. Now just look at 85. What does that represent? It represents total pregnant subjects, right? No matter whether they are test positive or tested negative, right? Total pregnant subjects. Okay, second one is total subjects. 15 represents total subjects not pregnant. No matter what test result is, not pregnant. And then this 84 represents total subject tested positive. Or you can just say that the total positive test results, right? And look at this one will be total subject tested negative. No matter whether they are pregnant or not pregnant, right? Whether they are not pregnant or not pregnant. Okay. And basically, that's how you break down this table. Now, let's take a look at this actual problem here. So let's say one subject is randomly selected from this table, right? Randomly selected. Find the probability of a subject with a positive test result. Given that she's pregnant, given that the subject is pregnant, given that the subject is pregnant. Now, basically, this language, given that, is very crucial here, right? To understand what we are trying to figure out here. And basically, we're looking at, you only look into this particular category of pregnant subjects, right? So basically, you look into this, all the pregnant subjects. Okay, so we know that it's 85, right? Total pregnant subjects, 85. And out of all those 85 pregnant subjects, what percentage of them has a positive test result? That's what this means. And that's what the conditional probability is about, right? So given this condition, this is very crucial. That's where you look into. Right? So in this case, we look into all the pregnant subjects, which is 85 here. And out of all the pregnant subjects, how many of them have a positive test result? We have 80 of them, 80 positive test results out of 85 total pregnant subjects. So here, if you want to write it, will be probability of test positive, given that it's pregnant. So one way to look at it is probability of test positive. Applying the formula intercept pregnant over probability of pregnant. And now you look at intercept or those two categories, test positive and then pregnant. And we know that will be 80, right? 80 over 100, we have a positive test result and also pregnant at the same time. And that's intercept. And that turned out to be 80 over 100. Okay. Probability, right? We're looking at probability. And then if you look at the probability of pregnant subject, we know that we have 85 pregnant subjects over 100. So it's 85 over 100. If you simplify this calculation, this is complex fraction. So turn the division in the middle to multiplication and flip the denominator. 100 goes on top, 85 goes on bottom. So it becomes, cancel 100, it becomes 80 over 85. Now, if you simplify further, it becomes, divide 5 on top is 16, bottom 17, right? 16 over 17. But if you just look at, like what I tried to analyze earlier, is since it's given that subject is pregnant, so we know that we look into the total pregnant subjects, 85, and out of 85 subjects, 80 of them test positive, and percentage of that portion of the subject will be 80 over 85, and that's more direct approach to solve the problem. So this conditional probability actually, when you look into the context carefully, it's constructed by when you have the table, get a total on both row and column, and you'll be able to find the result really quickly. Now I want you to try this. Let's say I have another question here, guys. So one subject is randomly selected. I want you to find out the probability of negative test result. No. Okay. Of pregnant subject, given that the subject is tested negative. So this is another conditional probability, right? Because it has a language given that. So now the given condition is the subject is test negative, okay? And then you want to find out that out of all of those negative test results, what percentage of the subjects are the pregnant subjects? Okay, so try that really quickly and to help you understand the conditional probability. So anybody want to share your opinion on this? All right, so again, we're looking at into this category, negative test results, right? So this is the main category. So we have total 16. And out of those 16 negative test results, there are 5 of them are pregnant. 5 of them belong to pregnant subjects. 11 of them belong to the project subject that are not pregnant. So we have a, so this conditional probability should be 5/16. So you're going to write like this: pregnant, given that it's negative. And without going to the applying the formula, we know that the intercept between those two categories, pregnant and test negative, will be 5. Okay, 5. And then given that the total of this negative test result is 16, so it's 5/16. Right. So you go direct to this result, or if you want to tackle that as using the formula, pregnant intercept. So this is equal to pregnant intercept negative, test negative, and divide by a probability of test negative. And we know that first one, the intercept between those two it's 5. So 5/100 over test negative is 16/100. If you simplify, it's 5/100 multiplied by reciprocal of this is 100/16. And if you cancel 100, okay, so we'll get 5/16. And as a result, okay. And that's pretty much everything for the lecture. And I can stay a little bit, right? If you have any question on your first couple projects, you can stay afterwards. I can give you some feedback, or I can tell you where they made a mistake, something like that. Other than that, you know, the class is over, right? If you do not have any question, feel free to go. Okay.
Thank you,
There's
Professor.
no Excel for today, right?
No Excel for today, yeah. And chapter 4 has no Excel project, but in chapter 5 we're gonna have Excel project. So,
Okay, perfect. Thank you. Have a good rest of your week.
you too. Have a nice week, guys. Bye-bye.
Thanks, Professor.
Bye-bye.
Thank you.
Bye.
Thank you.
Professor, I have a question.
Yeah, sure thing. Yeah.
So it's Ray, and I don't know if you remember, but like
Yeah. Right.
Yeah.
Yeah, you emailed me a couple times, right? About the homework, right?
about the math Excel was just like, it was so messed up. I
Okay.
ended up like emailing them a bunch of times, and they only ever, I had to tweet at them like on Twitter.
Okay. What did they
And,
say?
I finally got it fixed, so I was wondering if I could redo the quizzes that I missed, because it wasn't really
Definitely. Sure, yeah. I'll give you
So-
more time to work on it, definitely.
awesome. And then also, I just was looking at my grades yesterday, and I saw that my my Excel project 1, the file was corrupt. And then I went and looked at it on Excel, and that the actual file is corrupt, so I have to redo it. So
No
could
problem.
I
Okay.
resend that one too?
Sure, I will give you extension on that as well. So let me go in there. Let me extend the project. So you need the extension on both project 1 and 2.
No, I did project 2.
Okay, just project 1.
Yeah, project 1, and then the quizzes 1 and
Yeah. I extend the quizzes for you already. So
Oh,
you're good. And then let me extend the project 1 for you.
awesome. Thank you.
Yeah, no problem. Yeah.
Good rest of your
anytime.
week.
You too. Have a nice week. Great.
Bye.
I'm glad it works out for you, you know.
Yeah, it was so ridiculous.
Yeah. Quite a hustle.
Yeah.
All right.
a good one.
Sorry.
Okay, no problem. All right.
Can I please have help with like 3 of the chapter 3 questions? I'm just really confused.
On the homework, right?
Yeah, on the homework.
Definitely. Let me share the screen. Do you mind? I'm looking to your account.
No, not at all.
Okay, great. So really quickly, let me go to your account. Okay. Oh, right. And Shuya, right? Are you the one who asking the Neil?
No,
Neil,
it's
okay.
Nell.
Okay. All right, really quickly now. You're doing really good on the homework assignments and quizzes. Yeah, so it's from chapter 3. Yeah.
Yeah.
Let's review that.
So yeah, you could see I'm having trouble from question 10 to question 13 and then also question 18.
Okay. All right, coefficient
So
variation.
yeah, I put this in my Excel.
Mhm.
Well, I use Google Sheets. I put it in like all the numbers in and I did the equation and then I put it in and it was wrong.
Okay, no problem.
Let me go to my Google Sheets right now.
Yep, open that. I'm also trying to download the file, and I can show you really quickly how to do in Excel. All right, it's opening right now. So we just need to find out the mean and standard deviation. Then we can go from there. So first,
Yeah, so like what I got was
Mhm.
20.73.
Okay. Maybe just run the issues. It shouldn't be a big problem once you put into Okay. So now let me share the screen with this.
Says round to 1 decimal place.
Yeah,
Do you think that's
definitely.
why?
Yeah,
I got
that.
Okay, wait. Let me just see if that will work. If not,
No
I'll
problem.
let you know.
Let me know.
Second.
So we need to know the mean, standard deviation first.
Yeah, no, it says it's wrong still.
Okay, no problem. I'm gonna get it for you. So I'm gonna show you the solution right now.
Okay.
So it's standard deviation over the mean, right? So we need to know the quotient of those two. So can you see the Excel file?
Yeah, I could see.
Okay, very good. So now standard deviation first, we should do STD EV. It's a sample, so gotta be .s, right? Open that and highlight all the numbers. Look at that. And then we get a standard deviation and the mean, just average. Just like.
I think I might have been doing.
Mhm.
I think I might have been highlighting all of them.
Okay, no, the one column at a time, right?
Okay.
Yeah, so it's 2 things. So CV coefficient variation for the first data set will be standard deviation over the mean. So the quotient of this. Let me get if you turn it into 1 decimal, right? Is that what they want?
Mhm.
1 decimal, that should be, yeah, one more.
0.1.
Yeah, so it should be 6.9%.
Okay.
So for the first part, and let me see, percentage, you can just turn
Okay.
percentage.
Yes.